Here tonight, I want to start out by especially thanking Kent Center for inviting me out here and hosting this very nice event. I hope you've all been enjoying it a great deal. And also Leslie King, who contacted me and asked me if I would be able to come out. I very much appreciate the opportunity to come here. It's my first time in Greensboro. I live in Colorado. The talk that I'm going to do tonight is, the title of it is Beyond UFOs, based on this book here, and the subtitle is The Scientific Search for Extraterrestrial Life and Its Astonishing Implications for Our Future. And hopefully by the time I'm done you will understand why I gave it that title and what's so astonishing about this subject's implications for our future. I'm going to start though just by telling you a little bit about how I got into all of this, which is I was a child in the 1960s, and as some of you who were around at that time may recall, in the 1960s there was a lot of interesting things going on. On the one hand, we had the space program going, and for anyone who was interested in aliens, and of course aliens were in the media just as much then as they are today, for anyone interested in aliens, the space program was really changing the way we might look at it, because you just all of a sudden realize, wow, if we can do this, maybe somebody else can do it also. But at the same time, it was a very difficult period in which we lived in actual truth. We lived in constant fear that there might be a nuclear war that would annihilate us at any time. When I was in grade school, we had to hide under our desks in nuclear drills, as though that would have done anything for us. So you can see there was a lot happening, and as a young child at that time, putting those things together, I became convinced not only that there were aliens out there, but I was convinced that they were visiting me. I used to see them almost on a daily basis. I saw them coming into my room in what I thought were very, very tiny spaceships. And this is for real. I really, truly believed that I was seeing these tiny spaceships. And every night, I would wish that they would take me with them and show me what their lives were like and how we could solve our problems and avoid this nuclear catastrophe that I feared, and so on. Now, as I got a little bit older, I began to think, well, maybe what I was seeing wasn't actually alien spaceships, maybe it was something else. But I didn't lose my interest in the topic at all. In fact, when Apollo landed on the moon in 1969, my interest was really at, perhaps a high point. I decided, that was something I really wanted to do. I wanted to go to the moon. I went to see the movie 2001: A Space Odyssey with my grandfather shortly after it came out. How many of you have seen that movie? Okay, great. So some of the younger folks maybe haven't. You should watch it, even though it gets a little boring in places, but it's a great movie. It has this really incredible advanced alien civilization that really opened my eyes to another set of possibilities about alien life. But at the end of the movie, my grandfather turned to me and said, well, did you think that movie was realistic? And I said, oh no, of course not. And he, of course, assumed that was because, how crazy to have all these space stations and people with the colonies on the moon and everything else. He said, so was it because of all that space technology that you didn't think it was realistic? I said, oh no. That was the year 2001, and they hadn't even finished that big space station yet. Of course we'll be much farther along by then. So you can imagine my disappointment. Honestly, I would have to say the greatest disappointment of my life to date is that I have not yet been to the moon like I assumed I would have been able to do by now. But I kept in touch with this subject. I went on and studied astronomy in graduate school, got a PhD in astrophysics, and started teaching. I spent a couple years working at NASA headquarters in Washington, D.C., and was teaching lots of classes. When I went back to the University of Colorado, and through various strokes of luck, my class notes turned into textbooks, and I've been fortunate enough that I can now spend my days writing books and coming and talking to people, which is a lot of fun. And so tonight, I want to talk to you about some of the things that I have found most interesting in this topic. And I'm going to focus exclusively on the actual scientific research that's going on through NASA, through universities, and all around the world in this subject today. And I think it's quite amazing stuff, and hopefully you will find it that way too. Now, before we get into the modern understanding of this topic, it's worth focusing on the fact that this is not a new idea, alien life. This idea has been around for a very, very long time. And you can see I've chosen these two quotations here on the screen that go all the way back to ancient Greece. And I picked them because they both are talking about the possibility of alien life, and they both say essentially exact opposite things. The first one, from Epicurus in about 300 BC, Epicurus wrote, "There are infinite worlds, both like and unlike this world of ours. In all worlds there are living creatures and plants and other things we see in this world." This is quite interesting because here you have, more than 2,000 years ago, someone saying definitively, not just that there might be other worlds with life, he's saying there definitely are other worlds with life. Now you might wonder, how could somebody 2,300 years ago come to a conclusion like that? And I don't have time to go into much of the Greek philosophy, but I'll give you a very brief overview, which is that Epicurus was a follower of a more famous Greek philosopher named Democritus, who came up with the idea that the world is made out of indivisible atoms. And the Greeks thought there were 4 different elements: fire, water, earth, and air. And Democritus imagined that these 4 elements, when you broke them down, had these minimal sizes that he called atoms. That's where we get our idea of atoms from today, although our modern idea is a little bit different. And according to Democritus and Epicurus, the universe had begun with an infinite number of atoms of those 4 elements. And these had mixed about randomly, and he imagined, for example, that atoms of Earth were shaped like little jigsaw puzzle pieces, so if they banged into each other just right, they would stick. And thereby, Earth could grow. And over time, in this infinite number of atoms, you grew our whole world, the Earth. But of course, you know how the math of infinity works, right? If there's an infinite number of these atoms, then it must have happened an infinite number of times in the same way. So the fact that our Earth exists means there must be other Earths, and the fact that we exist means there must be other beings on these other worlds. So it was a natural conclusion for Epicurus and the other followers of Democritus. But now you look at Aristotle's counterpoint, about 50 years later, the world must be unique. He only gives a short quote because the rest of that quote's not as interesting. But I'll tell you what it means. Aristotle doesn't believe in atoms. He believes in the 4 elements, but he doesn't think they're made of these individual pieces, and he certainly doesn't think there was an infinite number of them. Instead, he believes that these 4 elements have natural motions, and when the universe began, they settled in according to their natural motions. And the natural motion of Earth, being the heaviest of the 4 elements, is to sink to the center. And therefore, all the Earth in the universe sank to the center and became our world. And for Aristotle, this is very nice. It explains, number 1, why Earth is the center of the universe, which of course is what they believed at that time. And number 2, it means there can't possibly be any other worlds, because if there was any other Earth out there, it would have sunk to here. So you have these 2 diametrically opposed viewpoints on the possibility of other worlds and other life, 2,300 years ago. And the debate continues. And it's quite amazing if you look into the history of this debate. It was an intense debate that went on and on and on. In the Middle Ages, in the Catholic Church, there were major theological discussions over this and what it meant to God and Jesus and his possibility of could he have gone to other worlds and redeemed them as well. You can find every major theologian going from 300 AD all the way up through the Copernican Revolution writing on this topic. And in all that time, the basic debate did not change at all from what it had been back in ancient Greece. And you might ask, why, with more than 1,500 years worth of people still talking about the same subject, why didn't they come up with anything new, and why did they keep arguing the same exact points? And the answer, in my opinion, is very simple. It's because it's possible to argue endlessly as long as there's no actual facts to get in the way. And the problem was, for all the talking they did during those 1,500 years, none of the facts ever changed. Why? Because they didn't have the ability to collect any new evidence or any new facts. And that is where science comes in. Science is where we try to get the evidence, get the facts, and finally be able to make a shift in the debate. And the first time that happened was in the 1500s and 1600s with what we call the Copernican Revolution. In 1543, Copernicus published his book in which he revived an ancient idea that had been proposed back around the same time as those quotes, and that idea was that the Earth is not actually the center of the universe, but instead a planet going around the sun. Copernicus revived that ancient idea and decided it made more sense to him than the idea of Earth being in the middle. And then over the next century, with the work of Tycho Brahe, Kepler, Galileo, and ultimately Newton, we found out for sure that Earth is a planet going around the sun, not the other way around. That was a fact that changed that ancient debate. Because remember, Aristotle's entire argument was based on the premise that Earth was the center of the universe and all the Earth had fallen here. As soon as we learned that Earth is not the center of the universe, Aristotle's argument fell apart. In other words, we had a couple of possibilities before, Epicurus and Aristotle's, but now we could rule out Aristotle's. Now, of course, that doesn't mean Epicurus was right. There might be more possibilities than just those two, but at least it allowed us to take one of them off the table. And that's why I like to say that science is, first and foremost, a way of distinguishing possibilities from realities. So what do we use science for? That's the first thing. We can think of all kinds of possibilities, and there's probably other possibilities that we can't think of. But for any topic, whether it's UFOs or extraterrestrial life or anything that we can think of, there's always going to be a lot of possibilities. Science lets us go through those possibilities and pick out, you know what, that one's not reality. Maybe another one, that one's not reality. And hopefully, eventually, we're left with one that might be real. And science, number two, is a way of helping people come to agreement. Now, that might sound a little strange when you think of the cultural wars that take place today around science, but if you think of this historical context, you'll see what I mean. Remember, for 2,000 years, almost everyone believed that Earth was the center of the universe. There were a few exceptions I mentioned in ancient Greece, but most people thought Earth was the center of the universe for 2,000 years. And then in a historical blink of the eye, a few decades, all of a sudden everybody changes their mind. How does that happen? It happens because at that point, in the early 1600s, the evidence had become so overwhelming that you could not possibly believe any longer that Earth was the center of the universe. And so science ultimately brings us to agreement. So I want you to just keep those two ideas in mind. Those, to me, are the two most fundamental points about science. It's a way of distinguishing possibilities from reality and a way of helping people come to agreement. Now, there's a lot more if you want to focus on the nature of science. If you read my book, there's a lot more detail on what we mean by science. But if you keep those 2 points in mind, I think it will really help. So now, I want to move on to the topic of what science tells us about extraterrestrial life today. Even aliens need a place to call home. Now, what do I mean by that? You know, if you watch Star Trek, you know they've imagined life in all kinds of different amazing situations. They've even imagined life forms living out in interstellar space. But scientifically, based on our understanding of life, at least as much as we can say about it, even if there are aliens that are living out in interstellar space somewhere, that's not where they started. As far as we understand it, life would have had to have started on a planet. Without a planet, you have no place for the life to begin. So you need to have planets in order to have life. And therefore, I like to break up the scientific discussion of the search for extraterrestrial life into what I call these three contexts: planetary, biological, and astronomical. Now, I'll talk to you a little bit about each one. Very briefly, the planetary context is, are there planets? Just in general. The biological context is, if there are, could we expect the same thing that happened here, meaning life, to happen there? And the third one is, and how many of them are there? So let's start with the planetary context. In 1995, that's not that long ago, right? In 1995, the number of known planets around other stars was 0. We had good reason scientifically to think that other stars would have planets, but we had no actual evidence of it. So some people still said, possibility, there's no other planets in the universe. And that was a real possibility in 1995. But then we got the new data, and we started to discover planets around other stars, so we could take that possibility off the table. And between 1995 and 2009, we discovered a number of planets around other stars. The number grew, and it was up around 300-400 in 2009. And then in 2009, we launched a mission called Kepler. And Kepler was doing a systematic search for planets around a set of stars in one particular spot in the sky. I may tell you a little bit more about how it does that later. But for the moment, Kepler was doing that search. You've probably all heard of the Kepler mission, and it has discovered an enormous number of new planets. Kepler has now discovered over 3,000 more planets during. It operated from 2009 through this year. It sadly seems to have died only about a month ago. But the data from Kepler has not yet been fully analyzed. Only about the first 2 years' worth of data have been studied. So that 3,000 planets is based on a small segment of the total Kepler data set. So that number 3,000 is going to grow. And what that means, number one, it means there are planets, right? That's our planetary context. There are planets around other stars. But number two, based on how many stars it's looking at and what it's seeing, we can begin to do statistics to say how common are planets. And here's a chart that shows you the results from just the first 20 months of Kepler's observations. And what these bars are showing you is the percentage of stars that have planets of these sizes. So for example, that first bar that goes up to about 17 shows that Kepler has found that at least 17% of all stars have a planet the size of Earth. Remember, this is only from the first few months' worth of data. If you extrapolate this out to what we will probably find as we go through the rest of the data set, among my scientific colleagues, the betting is that the end result is going to be that probably 95% or more of all stars have planets, and probably 90% or more have an Earth-sized planet. That's quite amazing, to go from less than 20 years ago knowing of 0 other planets beyond our own solar system to now being able to say with high confidence that planets are extremely common around stars. Now the second context is our biological context. That's the question of, okay, so you got a planet. Now those are just having the planets, but some of them are going to be in orbits where they, in principle, should have Earth-like conditions. If they're Earth-size and they have Earth-like conditions because they're the right distance from their star, will they get life on them? Now that's a much more difficult question to answer because we cannot look for life on any of these planets yet. They're too far away. I'll tell you more about that later. And so we have to understand the possibility that there's life on any of these planets by looking at how would life get started, and is it likely that that will happen? Now, one way to study that is in the laboratory, by trying to understand the building blocks of life that might be present on a planet like Earth when it's born, and there were lots of building blocks, and try to study the possibility that they will form into a living organism at some point. And based on those laboratory studies, it's looking more and more like life is probably pretty easy to get. For example, at Harvard, there's a guy who's doing this in his laboratory, and just putting in the natural minerals that were present and other ingredients that were present on the early Earth, and letting them sit around with some clay and ocean water and some energy, just like the early Earth would have had, he's gotten little miniature things that look like cells with RNA inside of them. Now, none of that RNA has been self-replicating yet, so it's not actually alive. But based on how far he's gotten in just a few years, it seems like nature, with the opportunity to do this all over the whole planet, trillions and trillions and trillions upon trillions of experiments, essentially just like his, that seems likely it would happen. We can't be sure until we know for sure, until it happens in the laboratory. But there's another way to look at this question, and that's by looking at the history of life on Earth. So this is a timeline that you see of the history of Earth. On the right end is the present, all the way back on the left is 4.5 billion years ago when the Earth formed. And what you'll see is that there's that little red bar near the top left, and what that red bar is showing you is what we call the heavy bombardment. This is the first 500 or 600 million years of the solar system's history, which is when the planets they formed, but things weren't really settled out yet. The planets have been forming from lots of things crashing into each other, basically. Much like what Epicurus had thought 2,000 years ago. So early in Earth's history, it was getting hit by a lot of big objects. So if you do the calculations, you'll find that every few million years, every few tens of million years, Earth probably got hit by something big enough to completely vaporize the oceans. Which means if there was any life living on Earth at that time, probably it would have been killed. So really, you don't have a good chance to get long holding life on Earth until that period of heavy bombardment ends. We know it ended about 600 million years after Earth formed. How do we know? We know by studying craters on the moon, because Earth and the moon were being hit by the same stuff. They're in the same part of the solar system. And by dating those craters on the moon, we know basically when that heavy bombardment ended. And then we look and say, well, what do we know about life? And you see right here, the earliest evidence for life on Earth goes back 3.85 billion years, which is right about when that heavy bombardment ended. In other words, almost from the instant, at least geologically speaking, that it was possible for life to exist on Earth, it was here. Now that doesn't prove anything, it's statistics of one. But if life was very difficult to get on a planet, you might think it would have taken a long time. If life is very easy to get on a planet with the right conditions, then you'd expect it to happen fast. Well, what we see is on Earth it happened for fast. And so that means it's at least hinted that other planets with similar conditions would also get life fast. So let's think about where we are. Number one, our planetary context tells us that planets are very common around stars, and a lot of those planets should have Earth-like conditions when they form. Our biological context tells us, and in that case, it seems like they ought to get life on them. So the only question remaining is, so how many places with life would that be if all this is correct? And that's where we get the astronomical context. And so let me start with the Milky Way galaxy. The Milky Way galaxy has somewhere between 100 billion and a trillion stars, and probably more on the trillion end, but let's use 100 billion because it's a nice easy number. We're finding that most stars have planets. So it seems very likely that there's 100 billion Earth-like planets in our Milky Way galaxy. Which means, based on what I just told you, if we're correct about how easy it is for life to get started, and remember it's an if, although it seems likely, then there's 100 billion planets with life in the Milky Way galaxy. So tonight, when you go home and you're thinking about all these aliens and stuff and you're having trouble falling asleep, don't count sheep, count stars. Or count planets with life on them. 1, 2, 3, 4. How long will take you to get to 100 billion? This is an interesting question because that's how many places there are with life in our galaxy if these ideas are correct. And the answer is, well, it depends on how fast you count, right? I like to use a counting rate of 1 per second. 1, 2, 3. If you ever do this with kids, and I've done this with kids a lot, they will immediately object. I can count a lot faster than that. What if you're Heisenberg? Say, well, very good, very good. But what about when you get to 86,398,444,341? Can you still say it in 1 second? And do you know what comes next? So you can see that counting to 100 billion at 1 per second is actually a pretty good rate. And therefore, it would take you 100 billion seconds. What's 100 billion seconds? Well, that's easy. You get your calculator later, and you divide by 60, and that turns it into minutes, and you divide by 60 again to turn it into hours, divide by 24 to turn it into days, divide by 365, and you'll find that 100 billion seconds is about 3,200 years. Think about that. Just to count the number of possible worlds with life in our Milky Way galaxy, just to count them would take you more than 3,000 years. And that assumes you don't go to sleep, don't take any breaks, and most importantly, don't die. Because that's a long time. And remember, that's only to count them. That wasn't to name them, to see which ones really do have life on or anything else. That's just to count them. And that's only the Milky Way galaxy. That's our galaxy. There's also 100 billion galaxies in the universe. You can put those two numbers together, 100 billion galaxies, each with 100 billion stars. Easy math, it's 10 to the 22nd powers worth of stars. What is 10 to the 22nd power? Now you understand why I have this picture up here. That's my son when he was very little on the beach in Hawaii. And what I had wanted him to do was to count the grains of sand in that shovel right there. As you'll see, he gave up after a little bit and just threw the grains of sand out. Which is disappointing because, you know, if you worked hard at a shovel full of sand like that, you could easily count every single grain in that shovel in maybe 2-3 weeks if you were diligent about it. And if you did that, then you could go count the rest of the beach, and then that beach, and then keep going around the island of Oahu, and keep moving. And here's your task. I want you to count every single grain of sand on every beach on Earth. Picture it. Why? Because if you do that, you would know how many grains of sand there were on all the beaches on Earth. Turns out, of course, you can estimate this number quite easily. And when you do that estimate, you will find that it is probably slightly smaller than that number of stars in our observable universe. Think about that. The number of possible worlds with life in our universe is greater than the number of grains of sand on every beach on Earth put together. When you think about it that way, the possibility that there's only one single grain that's got life on it almost sounds ridiculous. And so that naturally leads into the title of my book and the topic of this conference, which is, what are we seeing? Are there aliens visiting us? If there really are all these worlds with life on there, then it would seem like some of them should have developed civilizations, some of them should travel into space, some of them maybe should be visiting us. Are they? Well, that's the topic for the conference. That's not my topic. But it's useful to say, can we actually make any real scientific statements about aliens who would be visiting us? And the answer, interestingly enough, is that we can. And so I want to tell you next what I know about aliens, and by aliens in this case, I mean ones who might be visiting Earth. And actually, there's only one thing that I can tell you I know about these aliens, although I will give you 2 reasons for it. And the one thing that I know about them is that they are really, really smart. Now, how do I know that? Well, the first reason is because they come from really, really far away. Now, how do I know they come from really, really far away? Well, I know they don't come from our solar system. The reason I know that is because by now we have sent spacecraft to photograph every planet and every major moon in the solar system in fairly high resolution. And if there were any cities or anything like that, we have seen them by now. That means if aliens are visiting Earth, they don't come from around here. They come from some other star. Now, my favorite way of explaining this is to think about it in terms of a scale model. And so I actually spent a big portion of my career working on this project of building scale model solar systems. It took us more than 10 years from the time we proposed this until it was constructed on the National Mall in Washington, D.C. I don't know if any of you have gotten to see it up there, but next time you're in Washington, this is the National Air and Space Museum. This is the mall here with the Washington Monument over there, the Capitol back on this side. And if you walk out the steps of the Air and Space Museum, which are around there, and come down to the Capitol end, you'll see this pedestal here, which has this gold sphere right there, and that gold sphere is our scale model sun. So that is the sun at 1/10 billionth of actual size. So it's about this big, like a grapefruit. On this same scale, Earth is smaller than the ballpoint in your pen. And it's located about 15 meters, 16.5 yards away from the sun. So if I have the sun right here, you know, then the little tiny Earth is 15 meters away over here, something like this. Right, and it's going around that sun once a year, that little tiny dot. That's what our solar system looks like to scale. And so in this picture, you see Mercury there is the first pedestal, Venus, then Earth, and what these people are looking at is it's a glass disk on the pedestal, and the planet is inside the glass disk, that tiny little Earth or whatever planet you're looking at. And then you keep going, and there's Mars and Jupiter on one side of the steps and Saturn on the other, and keep walking and cross over the street, and you get to where the Hirshhorn Museum is. You'll find, go past there, and you get to the Smithsonian Castle, and that's where you'll find Neptune, and you'll also find Pluto, because we built it before Pluto got demoted. And so that's our solar system. It's about 600 meters, about a third of a mile from the sun to Pluto. So you can walk our solar system like this. Now you might be wondering, where's the moon? Well, the moon orbits Earth. On this scale, the moon is a little smaller than Earth. Remember, Earth is a little tiny ballpoint. The moon's even smaller, about a quarter of that size. And how far from Earth is the moon? The answer on this scale is right there. Earth, moon. Less than 2 inches. Think about that. On this scale, where you can walk from the sun to Pluto over a third of a mile, and we've sent spacecraft all out these distances, but human beings, right there, that's the furthest a human being has ever traveled. And only 12 people have done it. But now we're talking about aliens here, and they came from another star, not only taking you through our solar system, so you have to keep going, keep walking past Pluto. And the question is, when will you get to another star? And you might be thinking, how far do you have to keep walking? And so remember, you started here in Washington, D.C. You don't turn around unless you get to the end of the stage. Otherwise, you're backtracking, right? But you keep walking. So you walk and you walk and you walk. When will you get to the next star, Alpha Centauri? And the answer is, depending on how fast you walk, Forrest Gump style, a few months when you get to California. On this scale, the nearest star is across the United States. The entire distance across the United States, 2,500 miles away. And that's only the nearest star. We don't know that the aliens are coming from there. They might be coming from one much farther away. But think about that. If aliens really are visiting us, they're coming on this scale from a distance all the way across the United States, when this is the furthest a human being has ever traveled. That means they've got some pretty good technology. But that's only the first reason I know that they're really, really smart. The second reason I know they're really smart is because technologically they're at least about 50,000 years ahead of us. Now this is kind of an odd statement, and it's got a little bit of guesswork in it, but let me explain where it comes from. Now we don't even know, scientifically at least, if the aliens really exist, but let's say they do. Let's say that the chance of a planet getting life that eventually evolves into an intelligent civilization that can travel among the stars is really, really small. So small that it's about the same as your odds of winning the lottery. Only 1 in a million stars ever gets a planet with space traveling life. Sounds pretty bad, 1 in a million. But wait, there's 100 billion such planets in the Milky Way galaxy. You do the division, and you find out that means 100,000 civilizations that can travel through space in our galaxy alone. 100,000 other civilizations besides ours. But wait, it would be incredibly coincidental if one of them reached its level of space travel technology is at exactly the same time as us. The galaxy's been around for almost 10 billion years before our solar system even formed. There were plenty of opportunities for life to have arisen on worlds long before the Earth was even born. So what you'd really expect, if there are that 100,000 civilizations, is they would reach their space travel capability at random points in time, spread out over, let's say, the last 5 billion years. Do the division, and what do you get? You get that, on average, a new civilization rises up and becomes spacefaring somewhere in the Milky Way galaxy every 50,000 years. Right? That's what 50,000 years. Which means that if these other civilizations are out there and traveling through space, there's one thing that I can say about us relative to them, which is that, without doubt, we are the dumbest civilization out there. Because the second dumbest has a 50,000-year head start on us. And the third dumbest have a 100,000-year head start on us. And so on down the lines, the ones that have millions and billions of years head start. So in other words, if they survive and they keep developing their technology to space travel, the least sophisticated civilization that's visiting us is at least 50,000 years ahead of us, roughly speaking, technologically. So if you want to know what kind of technology they have, all you have to do is think of what kind of technology will we have 50,000 years from now if we keep developing it at the rate we've been developing it. And the answer is, of course, we have no idea. 50 years ago, nobody saw the internet coming. We don't know what our technology is going to look like 50 years from now, let alone 50,000. So what can we say about these aliens? They're really, really smart. What can we say about the technology they have when they visit us? The only thing I can think of to say about it is to fall back on a famous quote from Arthur C. Clarke, in which he wrote, "Any sufficiently advanced technology is indistinguishable from magic." And this, to me, is a very, very important thing to keep in mind when you're studying these phenomena, because as far as we're concerned, they're not really doing magic, they're really doing science and engineering. But to us, they're so far more advanced than we are that it's going to look like magic. To me, that means if somebody sees something and gets a quick glimpse of what they think might be an alien spacecraft and then can't get any solid evidence of it, that's exactly what I'd expect. Because maybe, because of the laws of physics, they can't hide from us all the time. Their cloaking devices go off once in a while. So we get a glimpse, but just not long enough to really grab anything. If somebody tells you they found metal parts on the ground in Mexico, we don't even build our own spacecraft out of metal parts anymore. We use all kinds of composite materials. They're not going to be building that. So you can use this to at least get some sense of what might count and what might not. But that's not my real topic. I want to go on and start talking about the actual search for life that's going on today. And so to do that, what we do scientifically is we say, well, we don't have anything to go on here, so we're going to start looking to see what can we say about the real possibilities of life out there on other planets. And the first thing we want to do is understand life on Earth. Because if you're looking for life someplace else, you better understand what it is you're looking for. So we start to study life on Earth, and we start getting hit by surprises almost immediately. The first thing is, if you're my age or older, when you were a kid, you learned that life was broken up into two major kingdoms, the plant kingdom and the animal kingdom. And then there were some microbes. Over the past few decades, people have been studying life genetically, looking at genetic sequences of different organisms, and building a tree of life based on genetic similarities and differences between different life forms. And this is the tree of life as we understand it today. And you'll see that in the past we said 2 kingdoms, right? Plants and animals. We now know there's actually 3 major groupings of life. We call them domains. They're called bacteria, archaea, and eukarya. And those 2 things that we used to think were the big kingdoms, plants and animals, we're both just 2 small branches of eukarya. In other words, most life on Earth does not look like us. It's a very interesting thing. If you're looking for life, don't go looking for us, because that's not what most life is. Most life's not like us. It also has a very interesting implication, which is, if you go back to my fears in the 1960s of nuclear war and so on, we used to think, oh, we're going to end the world and kill life on Earth with nuclear war. We're not going to do that. It's not that nuclear war is not possible anymore. It's that even if we blew up every nuclear bomb that we've ever built, oh yeah, we'd kill all of us. No doubt about it. Most life on Earth wouldn't even know anything had happened. It's living underground, deep in the ocean, microbes and so on. Nothing changed. Our existence matters little to most life on Earth. Kind of an interesting perspective on human power. We can destroy ourselves, but also humility. We can't destroy life on this planet. Now we apply that lesson to the search for life elsewhere, and what we find is life that seems extreme to us. We found life living in places like near volcanic vents where the water is superheated to over the normal boiling point of water, in highly acidic lakes here in Yellowstone. There is life, believe it or not. Believe it because it's true. There is life, microscopic life, that has been found living in the cores of nuclear reactors, where the radiation ought to be killing it almost instantly. And in fact, it is doing great damage to its DNA almost instantly. It's just that this life has evolved to repair its DNA faster than it gets killed, or faster than it gets broken down. So there is life in all kinds of different environments. The only commonality we have ever found for all life on Earth is that all life on Earth requires liquid water. And that means when we go looking for life in the solar system, our first focus is going to be, is there any liquid water or other liquids perhaps that could support life? And the amazing thing is, even right here in our solar system, although I've told you we're not going to find any intelligent life here, we might find microscopic life or other forms of simple life, and there's a number of places where that could be. Mars, Europa, Titan, Enceladus, and I'll tell you a little bit about a couple of these. Let's start with Mars. We know that we have a Curiosity rover on Mars right now. Why are we so interested in the possibility of life on Mars? The answer is that when you look at Mars from orbit, you see things like these craters that clearly have eroded edges by rainfall. This thing that looks clearly like a bunch of streams converging into a river. And this here, which clearly looks like a river delta. The colors are not real. A river delta as it comes out with mud flows and so on. And these are all obvious evidence of water flows, although they are all dry today. But they're telling us that Mars used to have flowing water on its surface. The Curiosity rover has been getting even more evidence. This is a lovely pair of pictures that were just released a few weeks ago. This is looking down at a dried up stream bed on Mars, and this is a dried up stream bed on Earth, and you look at the pebbles and so on, they look virtually identical. There's really no doubt, and the mineral analysis shows the same thing, there's no doubt that we are looking at a dried up stream bed on Mars. Mars used to have lots of water on it. It doesn't anymore. Today it's dry. Why today? It's got so little atmosphere that you can't even have liquid water out there if you want to. If you got out of your spaceship and took out a cup of water, that water would all either freeze or evaporate immediately. It's not stable in liquid form on Mars today because the atmosphere is so thin. But we know Mars used to have it. And the Curiosity rover is actually going towards this place called Mount Sharp, because here's a close-up view. The orbital studies had already showed us that this close-up view, as its cameras zoom in on where it's headed, the same idea. It appears to have sedimentary layers that date back billions of years that should enable us to learn a lot about the history or possible fossil evidence of ancient life on Mars. Now, Mars has no water on its surface today, But it may still have water underground, liquid water underground. It certainly has lots of ice, and we know it has some volcanic heat still, so it might still have liquid water underground. So you can imagine the possibility that if life got started on Mars billions of years ago, it's even possible that it's still there today. Now, we don't really know. Scientists like to bet. I have the good fortune of being able to do more than bet. I can write children's books about it. And there you see a page from my book, Max Goes to Mars, and this is the page where he sniffed out something with his special helmet attachment, and they dig down, and guess what they found? Microscopic life moving in underground water on Mars. Now, of course, this is fiction. We don't know if it's true, but if you ask me, that's what I think is going to happen sometime in the next 10 years or so. Probably not with dawn, but sometime in the next 10, 20 years, I think we're going to discover life on Mars. Europa is a moon of Jupiter. If you look at orbital photos of Europa, it looks like an ice ball with cracks in it. This is a very difficult scientific thing to explain. Scientists have really worked hard on trying to understand why Europa looks like an ice ball with cracks in it. And after great study, they finally came to the conclusion that the reason that Europa looks like an ice ball with cracks in it is because it is an ice ball with cracks in it. Which tells us that underneath those cracks there must be some liquid water ocean. In other words, Europa is apparently covered by maybe a few miles thick of ice, and under that is ocean liquid water, just like the water on Earth. More ocean water on Europa than on Earth. 2 to 3 times as much ocean water on Europa as on Earth. Now, we don't know what's in it because you can't see through the ice. Well, I get to write a children's book about that one too. And they take their little robotic submarine and they send it down and melts its way through the ice, goes into the ocean and starts looking. And I think we will probably find life on Europa someday too. Now, you can make energy arguments that suggest that life on Europa would probably also be microscopic and simple. But given that big ocean, it doesn't have to be. And just very briefly, I'll tell you a story that I used to. It says that there could be whales swimming in the European Ocean. And we had no way to know since we can't see through the ice. Now, I no longer will make that statement because I'm now sure there are no whales in the European Ocean. And the reason I'm sure is because one day when I gave this talk, an 8-year-old raised his hand at the end and said, "You said there could be whales in the European Ocean, right?" And I said, "Yeah." And he said, "And you said it's completely covered with ice." And I said, "Yeah." He said, "How do they breathe?" There could be giant fish in the European Ocean and we wouldn't know about it, but definitely no whales. And Titan is another amazing moon. Titan is a moon of Saturn. Titan has actually a thick atmosphere, and you look at this picture as we came into Titan with this lander, the Huygens lander in 2005, and I know it's hard to see from where you are, but what you see is basically dried up riverbeds again and so on as it was going down. And in fact, Titan not only has dry ones, it has actual lakes and seas on it of liquid, but not liquid water. It's too cold. The liquid is basically liquid natural gas, liquid methane and ethane. But it also probably has an underground ocean of water, much like Europa. So it's another possible place to look for life. But that's not why I showed you this picture. I showed you this picture because you can see the sequence as the Huygens lander set down. And this is the Huygens lander's view on the surface of Titan, looking out at these ice boulders laying on the lake bed. It's a dried up lake bed at this time. It's a seasonal thing. It probably gets its liquid methane and ethane at other times of the Titan seasons, which have a longer cycle because Saturn takes 27 years to go around the sun. But the amazing thing about this is Titan is about 1 billion miles away. If you imagine taking Titan at 1 billion miles away with what its actual size is and trying to view it to scale and aiming a spaceship at it and hitting it, it's the equivalent of taking a gun, firing a bullet, and hitting a dime when the dime is 2,500 miles away across the United States. We didn't just hit the dime from 2,500 miles away. Right as we got close to it, we slowed down and landed softly on its surface. That is amazing technology, even for a civilization as backward as ours. And it tells you what we are capable of when we decide to use our technology to discover things instead of for, say, blowing things up. In that sense, this is the picture that gives me hope for the human race. If we can do this, we probably can do a lot of other amazing things. Now, I want to get on to the parts that I think probably most of you are more interested in, which is all these microscopic primitive life forms in the solar system will be scientifically fascinating, but you won't be able to talk to them. If you want to have a conversation, we need something more sophisticated. We need intelligent beings that we can talk to. And therefore, as I told you before, we have to look to the stars. Well, one way of searching for these intelligent aliens is to study their planets and look for signs of them. Unfortunately, all the ways that we have of detecting extrasolar planets today, and I won't go through these all right now, you can maybe ask me questions if you want to hear more about the techniques later. But basically, all of our techniques are essentially indirect today. We know the planet's there, we can even measure its mass and stuff, but we're not getting a real picture of it, we're not getting much information about it. In other words, even though we know all these planets are out there, we are still a long, long way away from being able to study them in enough detail to figure out whether they have life at all, let alone intelligent life. And therefore, for the time being, our only hope of learning about other intelligent life is to make contact with them. One way might be if they're coming here and we get that contact, but the way we can search for it scientifically is through the search for extraterrestrial intelligence, the SETI program. That's listening for radio signals from other civilizations. Now, it's important to understand what we're looking for in this program. Of course, in principle, we'd like to talk to anybody out there, but in reality, our technology is pretty backward. You know that we have radio and television communications going out into space. So people on stars within 70 or so light years of our Earth, they could, in principle, our radio and television transmissions have been going by them. Now that means if there's someone in that area that has television that they're broadcasting, it'd be coming by us, right? The problem is our current SETI efforts are nowhere near sensitive enough to pick up our own radio and television from those distances. We couldn't do it. The only kind of signal that we could pick up with our current technology is a very strong signal beamed in our direction on purpose. Why would somebody beam a signal at us on purpose? Why not? If we want to know if they're out there, maybe they do too. So they send signals out. And if we're lucky, we'll pick one up. That's why SETI, in my opinion, is a very good idea. It's worth searching for it. Now, you might start thinking this through and say, gosh, you know, what if there's lots of other civilizations out there and they all build radio telescopes like this and they're all listening, but nobody's sending the big, strong signals out? Why wouldn't we just send the big, strong signals out? Well, it's a lot more expensive to send than to listen. You got to beam it and use a lot more power and so on. And therefore, you can imagine this terrible situation in which everybody in the galaxy, they're all out there, but they never know about each other because they just listen and nobody talks. So therefore, as a civilization, if we're going to listen, it's our duty to talk. Again, it's expensive. We've only done it a few times, but here's one famous example from the Arecibo radio telescope sent in the early 1970s. We beamed this message out into space strongly so that somebody listening could pick it up. It's a very simple message. It's encoded in binary so that if they know math, which they must if they're building radio telescopes, right, they can figure out and put this picture together. And if they're really, really smart, they'll figure out that they're looking at the radio telescope here, the person here, this is the sun, and this is the 9 planets, so they'll immediately know that we're liars because there's like 8 now. And that signal's going out. We've not heard back. But it's not too surprising because in order to increase the odds that somebody would pick it up, instead of beaming it at one star, we beamed it at the globular cluster M13, which has like 100,000 stars in it, which is good, gives you a lot more chances that somebody picks it up. The downside is it's 21,000 light years away, which means the signal won't get there for 21,000 years, and any reply will be another 21,000 years after that. Incidentally, there have been a few people who have said, this is a very bad idea. We should not be broadcasting signals like this into space, because what if the aliens out there are mean? And they get this message, they go, ooh, nice planet. Let's go kill them and take it. Now, actually, I promised some of Kent's family earlier that I'd tell you why aliens have to be nice. I think they probably are nice, but actually, it's not that they have to be nice. There could, in principle, be some mean aliens, I suppose. I don't really think so when I think through all the arguments. But let's suppose that there are mean aliens. I can still guarantee you that even if there are mean aliens, they will not receive a message like this where we say hello to them and broadcast it out and come kill us for that reason. How can I be so sure? Because remember, this is not the only kind of signal we're sending into space. We're also sending out radio and television. We don't have the technology to pick up our own radio and TV, but if they've got spaceships that can get here, they can watch our radio and TV. Watch TV, listen to our radio, I guess I should say, right? So if mean aliens do come and kill us all and take our planet, it won't be because of these hellos that we broadcast. It'll be because of something they saw on TV. But that brings us down to the bottom line question. If you go through everything I have told you about so far, I've said planets are extremely common. I've said it seems like life should be extremely common on those planets, although I'm not quite as sure that point is the first point. It seems like some of that life should eventually become civilizations and be able to build spaceships and be able to travel out there. And it seems like this should have been going on for millions or billions of years by now. Which begs the question of why don't we know it for sure? Some people think they know it, they've seen UFOs and so on, they think they've seen this, but it's not certain enough for everybody else to believe it. Why isn't it totally sure that there's lots of other aliens out there? Why haven't we found the absolute evidence for them? There's basically, well, there's a lot of possible answers to this question. This question is so famous that it even has a name. It's called Fermi's paradox, after the famous physicist Enrico Fermi, because he posed it in exactly this way at a lunch with other scientists in about 1950. Where are they all? And that was before we even knew that there were all these common planets out there. So the questions only become more serious over time. Where are they all? Well, I would argue that you can categorize all the possible answers to this question into basically three major categories. And remember, I told you that the subtitle of my talk in my book was "And the Astonishing Implications for Our Future." Now we're going to get to the astonishing implications for our future. Because I will argue that each of the three general possibilities of answer has astonishing implications to our future. The first possible reason why we don't see anyone, even though it seems they should be out there, is because even though it seems they should be, they're not. We are alone. Scientifically, this is still a possibility that's out there on the table because we have not proven otherwise. It could be that we are alone. Now, of course, I find it very, very difficult to believe when you think about those grains of sand, but so far we can't rule it out. If you look across all cultures, all religions, all theologies, one common thread that you will find, I believe, is that always one of the important goals of life as intelligent beings is to become self-aware, to be aware of what you mean to your world, to your God, to your universe, whatever it is that you're looking at. Self-awareness is a common theme of the purpose of life. Let's imagine that that's also the purpose of the universe, self-awareness. The universe has been around for 14 billion years. It's got as many stars as grains of sand and all the beaches put together. Does the universe know that it exists? Is it self-aware? The answer, of course, is yes. Right here in our heads. Before we found out about this less than a century ago, the universe did not know that it existed if we are alone in the universe. Right? We are self-awareness for the universe. And if we are alone in the universe, we are the only self-awareness that the universe has of its own existence. Which means if we were to destroy ourselves, it would not only be bad for us and our kids and the generations that wouldn't be born, we would be destroying something that the universe spent 14 billion years and all those grains of sand to finally achieve. You don't want that on your shoulders, do you? So don't destroy yourselves. Now, that's a possibility? Seems highly unlikely. If we're not alone, it's hard to come up with possible answers that would say, well, there's 2, or 5, or 10. Pretty much, you go instantly from either there's no others to there's 100,000 or more others. In other words, if we're not alone, then civilizations are common. So why don't we see them? Well, the second possibility is that they are very common, but no one has colonized the galaxy. But then you have to ask, well, why haven't they colonized the galaxy? There's no known physical barriers. Certainly the energy requirements of space travel are enormous, and I have some scientific colleagues who think that might prevent civilizations from traveling out among the stars. I don't believe it. I think with enough time, technology, and engineering, you can overcome any barrier that's not an absolute barrier. We can overcome that energy issue. So that's not what's stopping them, at least in my opinion. Another thing that might be stopping them is they don't feel like colonizing the galaxy. The problem with that is if they don't feel like it, it doesn't really make sense, because part of what we've learned through the history of science is that Earth is not unusual. It's a regular old planet. We're probably regular old life form, regular old civilization. Any civilization anywhere else would have had to evolve through the same kinds of evolutionary predator-prey pressures and so on. And so just like we would like to colonize the galaxy, not everybody wants to, but some of us would like to, and that means that if we get the chance, we'll do it. Which means if they get the chance, they'll do it. Doesn't seem reasonable to imagine they're special. So the only real convincing possible answer to why there could be so many civilizations but no one has colonized the galaxy is they never reached the technological level necessary to colonize the galaxy. I just told you that I think that given enough time, we will reach that technological level, and so would they. So why wouldn't they reach the technological level? Well, what if they destroy themselves before they get that far? And when you think about it, that kind of makes sense, sadly. The same technology that allows you to begin to do space travel also allows you to build nuclear bombs. That's going to be true for everybody. Maybe they all have nuclear war and wipe themselves out before they start to build spacecraft that can go to the stars. Maybe it's not nuclear war. Maybe it's just embedded hatred and cultural things like we see a lot of around our world today. Or maybe it's something a little bit more insidious. And with that in mind, I want to tell you very briefly about what I think is the #1 threat to our survival. Because it could be the same threat that wipes out other civilizations as well, if it does. And here's a picture of the threat. You don't even have to know what I'm graphing here, other than to see that I'm graphing time going back 800,000 years, and something that goes up and down naturally for 800,000 years. But then you see it shoots way up in recent times. Once I tell you that what this is it's the gas that regulates Earth's temperature, known as carbon dioxide, then you go, whoa. You mean for 800,000 years it never went above 280 parts per million and it's been shooting up? Yeah. People began to start to realize that this might be a real problem in the early 1940s and 50s, and therefore began to measure directly. All these old measurements come from ice cores, but direct measurements have been undertaken since about 1957 or 8. And when they started making those measurements, and at that time, the concentration of carbon dioxide in our atmosphere was about 315 parts per million. You can see it has been rising at a significant rate, and last month, May 2013, for the first time in at least 3 to 5 million years, it hit 400 parts per million. It is still rising. At this rate, it will be double the pre-industrial concentration by 2050, 560 parts per million, and keep going up from there. And this brings me to a very important point about this. Is this really a problem? If you listen to the news media, you'll hear people saying, oh, this is a hoax. I know right here in North Carolina, the legislature voted to not allow sea level to rise as a consequence of this, right? So what can we say about this? Is it real or is it a hoax? It turns out to be scientifically an incredibly easy thing to understand. You just start with two basic facts. The first fact is that carbon dioxide warms planets. That is not a guess, it's not a hypothesis, and you will not find a single scientist anywhere in the world who disputes this. Why? Because it's so easy to measure. You can measure the heat-trapping effects of carbon dioxide in the laboratory. That was first done 150 years ago. That's when people first started to get worried about this problem, 150 years ago. Not only for the other planets, but also for Earth. Unless you account for the warming effects of carbon dioxide, you can't correctly predict the planet's temperature. When you account for that in your models, you do correctly predict planet temperatures. So there's no doubt that carbon dioxide warms planets. So the bottom line is, we have an obvious conclusion. We're causing global warming, and we're going to keep making it worse as this goes up. This is not hard. It's not difficult to understand. It's not really in any dispute. The only people who dispute it are people who are not paying attention to these very, very basic facts. And that brings me, with this alien civilization idea in mind, to this very important quote, because this probably describes not only us, but every alien civilization that's ever existed or exists. Human history becomes more and more a race between education and catastrophe. Are we smart enough to figure out what we're doing that could cause our own demise and stop it before it's too late? The picture I've chosen here, incidentally, is from another of my children's books, The Wizard Who Saved the World, where we're building solar panels in space. You know, we don't have to keep burning fossil fuels. Solar energy, people say, hey, you know, it's hard to use, it's cloudy, it's dark. Not in space. Just put a bunch of solar panels in space, beam the energy down to Earth, problem solved. It's really not that hard. It's a matter of believing that we have the problem to solve and the willpower to solve it. What if the other civilizations don't destroy themselves? What if they keep developing the technology and they do go out and have space travel and colonize the galaxy? If they didn't destroy themselves, then they're out there. They have a galactic civilization. It already exists. Think about this. The first possibility that I told you about is that we are alone. Possible? Yes. Likely? Hardly seems so. The second possibility is that there's lots of civilizations out there, but they all destroy themselves before they can colonize the galaxy. Possible? Yes. Likely? Maybe. I mean, it certainly seems like we're going to have a hard time getting past where we are today. But gosh, we sure hope that's not right. Because if it is, not only does it mean there's nobody else out there visiting or traveling around, it would also mean our odds are pretty bad, right? If 100,000 other civilizations have gotten to this point and not a single one of them has ever made it through, what's our chances? Maybe we'd be lucky and be the first, but that just doesn't bode well. We hope possibility number 2, that they all destroy themselves, is not correct. Possibility number 1, unlikely. Possibility number 2, we hope it's not true. All we're left with is they're already out there. There's a galactic civilization around us today. And that brings me to the final points here, which is that we live at an incredible time, especially for the young people in the audience today. You have a burden upon you that no previous generation has ever had. You know, you even go back to World War II. We did a lot of damage in World War II. We could not destroy ourselves at that time. We didn't have enough bombs to completely destroy ourselves. We could certainly do a lot of damage, but we couldn't destroy ourselves. Now we can destroy ourselves, not only through bombs and nuclear war, but in these other ways that we've talked about. We're the first generation in history with the power to destroy everything that has come before us. But we're also the first generation in history that can chart a path that will send our descendants to the stars. And it is this generation alive today that will make that determination, because I believe that if we can get through the next 50 to 100 years, the only way we survive that long is if we're smart enough to figure out ways to make sure we won't wipe ourselves out. And once we've done that, we're home free to head for the stars. So this is it. This generation today decides the entire past, present, and future of the human race. And that brings me to the final question is, will we, this generation today, prove that there is intelligent life on Earth? And that's an answer we'll only know after we see how we do these next 50 to 100 years. So that's the end of my talk. These are some of my books there. The textbooks are down at the bottom. Beyond UFOs, I have a few copies here available in the back for $20. I think I've got 10 total if anybody's interested. And just not to brag too much, but I'll tell you my greatest honor with this one was Miami University of Ohio picks one book for all incoming students to read each year. If you look at their list going back, since they've run that program 25 years, it includes George Orwell, Kurt Vonnegut, Toni Morrison, David Eggers, Elie Wiesel, and so on. And this was their choice 4 years ago. So every one of their 5,000 students read that as their incoming project. Math for Life is out, and What is Relativity will be out next spring. And then you saw, oops, get that back for you. So I want to tell you about this just because I think it's fun. There we go. And so you know I have my children's books. There's a set on display back there. I don't have any available to sell, but you can get them from Amazon or wherever. And what I find, what I'm particularly excited about is that my books got picked recently. They are all going up on the Orbital 1 launch this December to the International Space Station, where they will be read by the astronauts in orbit. Videos posted online for teachers anywhere in the world to watch with their kids for free. So that is it. Thank you very, very much.